Yes, good morning again. So this is our second video related to additive manufacturing. In the first video, we discussed about the basics of additive manufacturing. What is the definition of additive manufacturing? What are the different terms associated with additive manufacturing? Then what about the capabilities such as geometry capability and material capabilities of additive manufacturing? Then the different classifications as per ASTM, American Society for Testing and Materials. Then based on the raw material, the additive manufacturing is classified into solid, liquid, and gas. Till now, gas is not used as a raw material for 3D printing process, but solid and liquid raw materials are using to prepare the real physical model the for the preparation of real physical model using this technology. So today we will deal with the solid modeling concepts with using different various packages and its basic concepts. Then the STL file, its importance, the different formats such as ASCII format and binary format. Then so these are the important relevant points of today's lecture. So coming to the solid modeling, what is solid modeling? Solid modeling is a technique used in computer-aided design to create 3D models with geometric accuracy. The process involves creating a virtual model of the object which can be manipulated and viewed from various angles to ensure that it meets the desired specifications. Solid modeling is considered to be the most challenging aspect of CAD as it requires the software to simulate the object from both the inside and outside. Solid modeling is used in a variety of industries, including engineering, architecture, product design, and manufacturing. It allows designers and engineers to create complex shapes and structures with precision and accuracy, which can be difficult or impossible to achieve with traditional drafting methods. One of the key benefits of solid modeling is that it enables designers to make changes to the object on the fly without the need to start from scratch. This can save significant time and effort as well as reduce the risk of errors or mistakes. To create a solid model, designers typically start with a 2D sketch, which is then extruded, revolved, or swept to create a 3D object. The object can then be refined and modified as needed using a variety of tools and techniques. Overall, solid modeling is an essential tool for modern design and engineering, allowing for the creation of complex, accurate, and detailed objects with ease. Then we will enter into the STL file. We already discussed in the first video about the STL format. Once again, what is STL format or STL file? Stereolithography. It is commonly abbreviated as STL, is a highly popular 3D printing method that has been in use for a long time. It is also known by its alternative names, standard triangle language or standard tessellation language. At its most basic level, STL is a file format used to describe the surface geometry of a three-dimensional object. More specifically, an STL file represents an object as a series of interconnected triangles which together define the object's shape and surface characteristics. These triangles are arranged in a way that ensures the object can be accurately recreated using 3D printing technology. Overall, STL has become an essential tool for creating and sharing 3D models, and its versatility has made it a favorite among designers, engineers, and artists alike. Then, next is the geometry versus topology. Geometry is it's a branch of mathematics that studies the quantitative properties of space, such as distance, angle, size, and curvature of figures on manifolds. It deals with the measurement, properties, and relationships of points, lines, angles, surfaces, and solids. Geometry has been studied for thousands of years dating back to ancient civilizations like the Greeks and Egyptians, and has numerous practical applications in fields such as engineering, architecture, and physics. Topology, on the other hand, is a branch of mathematics that concerns itself with the qualitative properties of space. It is the study of the properties of space that remain unchanged after under bending, twisting, stretching, or other continuous transformations. Topology is often described as the geometry of rubber sheets because it studies properties of objects that can be deformed and stretched, but not torn or glued together. Topology is an abstract and highly theoretical field of mathematics, and its concepts and theories have numerous applications in computer science, physics, and engineering. Some examples of these applications include the study of the properties of networks, the design of algorithms, and the analysis of data structures. Geometry deals with quantitative properties of space, such as distance and curvature on manifolds. Topology deals with more qualitative properties of space, namely those that remain unchanged under bending and stretching. Then the different types of solid modeling approaches are constructive solid geometry, then boundary representation, feature-based modeling, etc. So these are the different types of various approaches that is used to create the solid models. Then what is constructive solid geometry? Constructive solid geometry is a powerful modeling technique used in computer-aided design systems. It involves the use of simple geometric shapes such as cubes, spheres, cones, and cylinders to create complex 3D models. The technique works by combining these basic shapes using Boolean operations such as union, subtraction, and intersection. In constructive solid geometry, the basic shapes are considered as building blocks, and the Boolean operations serve as the tools to manipulate these blocks. For instance, the union operations combines two or more shapes to create a new shape. The subtraction operation removes a volume from one shape using another shape. The intersection operator creates a new shape by taking the common volume between two shapes. One of the advantages of CSG is that it allows designers to create complex models quickly and easily. Instead of starting from scratch, designers can use basic shapes to build their models. Additionally, it provides a way to modify parts of a design without having to recreate the entire model. Constructive solid geometry is commonly used in fields such as architecture, engineering, and product design. It is also used in computer graphics for creating 3D models that can be used in animations, video games, and virtual reality simulations. Then next is the boundary representation or BREP. Boundary representation or BREP is a popular method for CAD modeling. It represents a solid surface by defining its boundaries as a collection of interconnected geometrical entities. These entities include faces, edges, and vertices, each having a specific topological relation with the others. In a BREP model, a face is a two-dimensional entity that can be planar or curved. An edge is a one-dimensional entity that defines the boundary between two adjacent faces. A vertex is a zero-dimensional entity that represents the endpoint of an edge or the intersection of two or more edges. Each of these topological components has an associated geometric definition. For instance, surface defines the shape and orientation of faces, curves define the shape of edges, and points define the position of vertices. The connections between these components are also crucial in BREP model. They describe how the faces, edges, and vertices are connected to one another, thereby forming a solid or surface. The topological and geometrical information in a BREP model can be used to perform various operations such as rendering, analysis, and manufacturing. Then another technique is called a feature-based modeling. So the dedicated CAD packages such as SolidWorks, Fusion 360, Inventor, all are using this type of feature-based modeling approach. When it comes to creating 3D models in a computer-aided design or computer-aided manufacturing software, feature-based modeling is the most commonly used method. This approach involves defining the geometry and topology of the model by adding and subtracting specific features. These may include sketches, which serve as the foundation for the model, extrusions, which create solid shapes by pulling a 2D shape along a defined path, fillets, which round off sharp edges, holes, which create openings in the model, and patterns, which enable users to replicate features across a surface or object. By leveraging these features in various combinations, designers can create highly detailed and complex models with a high degree of precision and control over the final product. Different packages having control. Yeah, different packages having options to convert the CAD model into STL format. So here in the screen you can see I am converting the CAD model from Autodesk Inventor to STL format. Click Save and save as change the save as type to STL format, and you can convert the CAD model into the STL format. Feature-based modeling. The best example is SolidWorks, Inventor Professional, the Fusion 360, etc. Tinkercad is a cloud-based application. It's an application. This is again this is a simple 3D application to prepare models for 3D printing. Tinkercad is using constructive solid geometry approach for preparing the 3D models. Then we will enter into more details about the stereolithography and standard tessellation language, means STL format. STL is the format we are using in the file preparation of 3D printing. STL means stereolithography or standard tessellation language or standard triangle language. Stereolithography is an advanced additive manufacturing technique that allows for the production of complex parts and shapes with a high degree of accuracy. This technique involves using a vat of liquid UV curable photopolymer resin and a UV laser to build parts one layer at a time. The process starts by creating a 3D model of the desired part using computer-aided design software. The software then creates an STL file, which is a digital representation of the part that can be read by a stereolithography machine. Once the STL file is loaded into the machine, the process begins. The machine uses a laser to selectively cure the photopolymer resin in the vat, building up the part layer by layer. As each layer is completed, the build platform moves down a fraction of a millimeter, and the process is repeated until the part is complete. The STL format is widely used in the 3D printing industry and is named after the stereolithography process. It is also referred to as standard triangle language or standard tessellation language. The file format represents the surface geometry of a 3D object using a series of interconnected triangles. A tessellation is also known as tiling. It is the process of covering a surface such as a plane or a wall with geometric shapes without any gaps or overlaps. In stereolithography, tessellation is used to represent the curved surfaces of a 3D object using a series of flat triangles. So in STL file, we are using flat triangles. This technique allows for the creation of complex shapes and surfaces that would be difficult to produce using traditional manufacturing techniques. This image, this is the image of a triangular pyramid. This is the triangular pyramid, and this is the ASCII format. This is the ASCII format of this triangular pyramid. Here we know that how many triangles? 1, 2, 3, 4 triangles. In the format, ASCII format, you can see the format starting with solid, and then after that the name of the object. Here the name of the object is triangular pyramid. Then you can see the 1, 2, 3, 4. These are the 4 details of the 4 triangles. Okay, this is one triangle, this is another triangle, this is third triangle, and this is fourth triangle, and finally there is an option called the end solid. So this is a See, just imagine this is a simple triangular pyramid and this consists of this much codes. If the object is complicated, the number of lines is too high, so it's very difficult to handle, or it's very difficult to work with the ASCII format. That's why we are using by either. So we can use either binary format or we can use ASCII format. So this image is representing the ASCII format of a triangular pyramid. Yes. Yeah. So STL files are commonly used in the 3D printing and computer-aided design application. An STL file is made up of a sequence of connected triangles that describe the surface geometry of a 3D model or object. Each triangle is defined by 3 vertices that specify its position in 3D space. The triangles are arranged in a particular order to form the surface of the object. The density of triangles used in an STL file is determined by the intricacy of the design. A more complex design would require a higher triangle density to capture all the details accurately. Therefore, the resolution of the 3D model increases as the triangle density increases. You can quickly identify an STL image by its file extension, which is .stl. Additionally, an STL file lacks any color or texture, as it focuses solely on the shape and structure of the object. STL files can be easily imported into 3D printing software, where they can sliced into layers and printed layer by layer to produce the 3D object. Then, coming to the ASCII format, an ASCII STL file starts with the line with solid name. As I already mentioned here, you can see solid triangular pyramid. So ASCII STL file start with the line solid name. The name part is actually optional, but there must still be a space after solid if the name is omitted. This is for compatibility with some software. The rest of the line can be ignored and is sometimes used to store metadata like the file name, author, or modification date. After the first line, there can be any number of triangles, each represented as follows. Each n or v is a floating point number in sign Mandisa e-sign exponent format. For example, 2.64800 e minus 002. The format of the file suggests that the other possibilities exist, such as facets with more than one loop or loops with more than 3 vertices. However, in practice, all facets are simple triangles. White space can be used anywhere in the file except within number or words. The spaces between facet and normal and between outer and loop are required. The file ends with the line n solid name. Then coming to the binary format, as I already mentioned, when dealing with the 3D modeling files, ASCII STL files are commonly used to represent the surfaces of an object using triangles. However, the problem is these files can be very large in size, making them difficult to handle and work with. To address this issue, a binary version of the STL exists. A binary STL file includes 80 character header that is typically ignored by software. However, it's essential to note that the header should never begin with the ASCII representation of the string solid. If it does, some software might mistake the file for an ASCII STL file, leading to potential confusion. After the header, there is a 4-byte little Indian unsigned integer that indicates the number of triangular facets that are present in the file. This information is vital as it allows the software to know how many triangles it needs to read to render the object correctly. Following this, the data contains information about each triangle in the file, including its normal vector and vertices coordinates. It's worth nothing that the binary STL format is more efficient than the ASCII format in terms of the file size and processing speed. However, modifying binary STL files can be more challenging than modifying ASCII STL files. If we want to modify ASCII STL files, that is easier than binary STL files. The file simply ends after the last triangle, making it easy to read and work with. Then we will enter into the details of resolution. This is again a very relevant term related to the STL file. The resolution of an STL file, which refers to the level of detail captured in the model. In the screen, you can see three types of images. The first image is representing too much resolution, and the middle figure is representing that the meshing is correct, and the final image is representing that the STL file resolution is too low. So the resolution refers to the level of detail captured in the model, plays a crucial role in determining the quality of the printed part and the time required to slice the model. A model with a high resolution will have an increased level of detail and a smoother surface finish, resulting in a better quality print. However, the higher the resolution, the longer it will take to slice the model, as the software will have to process a greater number of triangles or polygons. This increased processing time can make printing large or complex models more time consuming. Therefore, it is important to find a balance between resolution and processing time to ensure optimal printing results. Then, coming to the surface deviation and normal deviation concept. Again, this is very relevant. These two terms are very relevant while working with the preparation of the STL file. Surface deviation. When it comes to 3D printing or CAD designing, the surface deviation and normal deviation in an STL file play a vital role in ensuring the final product's accuracy and quality. The surface deviation, here in the image you can see 1 represents the surface deviation and 3 represents the normal deviation. And this dotted line represents our actual model, and this line represents the triangle STL format. STL triangle, the n number of triangles that is in our CAD model. The surface deviation and normal deviation in an STL file play a vital role in ensuring the final product's accuracy and quality. The surface deviation refers to the difference between the actual surface of the model and the ideal surface. This deviation can occur due to various factors, such as inaccuracies in the scanning process or errors in the CAD model. On the other hand, the normal deviation, the number 3 represents the normal deviation. The normal deviation refers to the angle between the normal vector of each triangle in the model and the ideal normal vector. Normal deviations can cause issues like gaps or overlaps in the final printed or machined part. Therefore, it is essential to ensure that the surface deviation and a normal deviation in an STL file are within acceptable limits to avoid any potential issues in the final product. It is recommended to set the tolerance between the deviation tolerance or the surface deviation between 0.01 mm to 0.001 mm. When we will work with the Inventor Professional in STL 3D printing environment, click here print option. When we click the print option, you can see the resolution. Here you can see the surface deviation and normal deviation. Now you can see the surface deviation is point. So I will change the surface deviation to 0.01. Okay, and I will click OK. Again, I will show you print options. Here you can see the format. Here the two formats are mentioned, either binary format or ASCII format. And the surface deviation, I have entered the value as 0.01. It is the recommended value. Either the recommended value is to set the tolerance between 0.01 mm or to 0.001 mm. That is the recommended value of tolerance. Then again go to print options. Then the normal deviation, you can change the normal deviation also. Again, the recommended setting for this parameter is as low as possible. So I will change this into 10. So the recommended value is keep the value as low as possible. Okay. So So we have learned about the solid modeling concepts, different solid modeling approaches such as constructive solid geometry, boundary representation, then feature-based modeling, different CAD packages such as SolidWorks, Inventor Professional, Fusion 360 are using the feature-based modeling approach, whereas Tinkercad is the best example of using constructive solid geometry. Then coming to the STL file, ASCII and binary format. Then finally, the three very relevant terms such as resolution, standard deviation, surface deviation, and normal deviation. So next video we will deal with the different manipulations of STL files. Thank you.